Hello, Class 12 Physics, Chapter Dual Nature of Radiation and Matter. In this chapter, we are going to study that whether light is a particle or a wave. And then we will come to a common ground that it is both matter as well as wave. And also we'll come to know that all the objects around us moving are not only particle, but they also behave like waves. So all of it, but we'll start from the uh, from an experiment which is called photoelectric experiment, photoelectric effect. And before that, we will try to understand about electron emission. Electron emission from metal surface. So basically we have four ways to eject electron, remove electron from a metal surface. So these are, first one is thermionic emission, second field emission, third, actually the third one should be fourth, but I'm putting it as third, secondary emission. And fourth, photoelectric emission. Thermionic emission is the electron emission from the metal surface due to supply of heat by heat energy. Field emission is the electron emission by strong electric field. Secondary emission. Okay, but before secondary emission, I will come to photoelectric emission by radiation. And as the name is photoelectric, photo refers to light. So radiation, and that's too which lies in visible region. And secondary emission by the collision of primary emission. Primary emission of electrons. So the electron which emit on a primary basis by heat, strong electric field, or radiation. So those electrons, when collide with other neighboring electron, so those secondary electron also emit. So that is called secondary emission. So well, here we are not going to study about these three, but this one. And what is this doing in this entire chapter? Yeah, there is a connection of this photoelectric effect and this dual nature of radiation and matter, and we are going to study it. You will see that it is going in completely different direction, but yeah, there is a relation of this photoelectric effect with this chapter, dual nature of radiation and matter. I will tell you about it later on. Now, what is important in all of these four types of emission is some kind of energy supply to that metal. We know that an atom, a metal, if we talk about a metal surface, so it consists of number of atoms. So it will be an atom, and we know that nucleus is tightly held with strong nuclear forces, and electron orbit that atom, and so on. The outermost electron are less loosely bound than innermost energy levels. So it is easier to supply this outer energy level electron some additional energy, and that energy can be supplied through heat, strong electric field, collision of another electron, or photoelectric radiation. So that energy can be supplied to that electron, and that electron can be knocked out. This is not a kind of ionization. Yeah, it is, but in a different manner if we talk about this metal. So we have to not only remove this electron from this atom, but also we have to remove it from entire its structure, from entire its environment. So this electron should, if we supply some energy to it, it should get removed from the surface. So we require enough energy to remove it, and that energy, minimum amount of that energy, is called work function, and that is the first building block of this chapter. So we'll talk about work function. Its symbol can be given by W or phi. So the minimum amount of energy I have quoted, especially photo energy. If someone asks me, or in the exam it is asked that what is the work function in terms of photoelectric effect, then we should use photo energy term. Or in general, if it is asked, then we have to use this energy term in general. This is a generic term. It is specific for photoelectric emission. Required to eject or remove electron from metal surface is called work function. So it is the minimum energy, how minimum energy you can give and electron can be taken out. That is work function. So means we can't say the amount of energy required to eject, because we can supply enormous amount of energy. So a minimum limit. What is that minimum amount of energy that can be supplied, and we can eject an electron from the metal surface? That is called work function. Okay. Next, if we talk about this photoelectric emission, then there is an important term which is directly related to this work function, and that is called threshold frequency. Its symbol nu subscript naught, or f naught, but I prefer nu naught. So here it is. The minimum frequency of radiation, especially light, required to eject an electron from metal surface is called threshold frequency. So you can see there is quite common words in both the definition, because radiation also carry energy. According to Planck's hypothesis, E equal to h nu, and it is well accepted one. So we can say in the same way there is an energy associated with this nu naught, and that will be the minimum energy required to eject electron. So it is turning out to be definition of work function. So we can say, so work function, how work function has came here, because there is a symmetry in both terms. This is only we are talking about frequency, but it must have some energy associated with it, and that is work function. Work function phi is equal to h nu naught. It means if we supply, actually this is not the work function, this is the energy carried by that light photon of threshold frequency, and this is enough energy to eject electron from metal surface. So the same energy is equal to the work function. That is why phi equal to h nu naught. So this is how we can write it. The relation between, we can write relation between work function and threshold frequency. This is the relation. Next, in the same account, there is threshold wavelength. Lambda naught. So this time situation will change, because the relation between nu and lambda is in inverse proportion, nu equal to c by lambda. So threshold wavelength lambda, it must have something definition with some opposite word, that of threshold frequency. So here it is the maximum. See, here was minimum, here was minimum, here is maximum. And guess what? Why is it? Because it is in inverse proportion. If we talk about the term energy, then it will be hc by lambda. So that is why it is inversely proportional to energy, it is inversely proportional to frequency. That is why for work function we use the term minimum amount of energy, for threshold frequency we use the term minimum frequency, but for threshold wavelength we are using minimum wavelength of radiation or light required to eject electron from metal surface is called threshold wavelength. And therefore we can write its relation with work function as hc by lambda naught. So there are four numericals, and you can see we know the value of h, we know the value of c, but here I have written h in two different ways because sometime in the exam it comes in this way. So sometimes they can give the value, this thing we know, but they can give the value h upon e. They can put it in the denominator. H upon e is 4.14 volt second, and at that time you will get confused that how to use this value. So that value can be used in terms of electron volts, and in the same way hc, direct multiplication gives this value, but in terms of electron volt meter it will turn out to be this in nanometer in angstrom. So uh, they can give these values, or you can memorize these values as well. There's no issue memorizing these, because at that by doing so you can be able to, just you have a question and you can directly solve it without any trouble. So okay, so we'll use these constant wisely. First, if threshold frequency for metal surface, this one, then find work function. So we know phi equal to, I'm taking it as two different questions, so I'm not going to convert joule into electron volt. I'm taking these question in two different ways. So phi equal to h nu naught. First, I'm finding out this work function in joules. So I have to use this value in terms of joule second. So it is 6.62 into 10 to the power minus 34 into nu is 4 into 10 to the power 14. We can multiply this, we can get the answer. So it is 2 4 8, 24, 26. 26.48 into 10 to the power minus 20 joule. We can convert it into electron volt by dividing it by electronic charge, that elementary charge E equal to 1.6 into 10 to the power minus 19. We can do that. But if we could directly use this value, then phi equal to h nu naught, and h is 4.14 into nu naught, 4 into 10 to the power 14. Oops, there is a slight error. This is not complete value. It should be multiplied by 10 to the power minus 15. So correct this in your notes. Well, I missed that, and also here. So multiplied by 10 to the power minus 15 will also be there, into 10 to the power minus 1. So that will go into denominator, and decimal place will shift to one place, 1.6. That's enough, 1.6. After rounding off it will remain that this way. So electron volt. So this is all of it. So remember this thing, h is this one. All right, so here if threshold wavelength of radiation, okay, now what I'm going to do, I'm finding out it in electron volts only. So you can do that joule part, and I'm doing for electron volt part. So phi equal to, it is not the power or something, I've just taken out that I'm working on electron volt. So hc by lambda, lambda is in nanometer. It is better to use this value this time. There is no other power included there, that in these values, so we can directly use that. 1242 electron volt, whatever. So finally it will come out to be electron volt, because in the denominator it will also come with nanometer, and nanometer will get cancelled. So this is the value, and upon 800. That's all. Two decimal place will go here. So 8 ones are 8, and approximately 8 fives are 1.5 electron volt. So now this one, if threshold wavelength metal surface, this one. Okay, so here this value will be used. Once again I'm using for electron volt part only. So phi equal to hc by lambda, and hc is 12,420 upon 5550, and 0 0 will get cancelled. 5555, do you know the table of this? At least 2's are. I'm doing rough calculation, approximate calculation, so my answer can be okay, 2's are, and again 2's I think so. So you can do it in a correct way, so you can get it easily. If work function is 4 electron volt, then threshold frequency. So here phi equal to h nu naught. So we have to find nu naught. It is better to use phi is in electron volt, so it is better to use electron volt value of h. So phi is 4 electron volt upon, here it is, 4.14 into 10 to the power minus 15. If you divide this, then it will be something like 0.99. I'm guessing this. You can divide and you can find the answer. And we'll take this in the numerator. So it will be 10 to the power 15 hertz. Shifting decimal one place, 9.9 into 10 to the power 14 hertz. Or in a different way, you can also do it like this is electron volt. So you can multiply it with electronic charge, and then you can put value of h of this value. So still you will get the answer, but I think if you could memorize these values, so you would not be depending upon the values given in the exam, and you can easily get these answer in instantly. So all right, so we proceed to next topic. All right, experimental arrangement to study photoelectric effect. I am drawing this diagram. Um so you people should also side by side draw it. It is not better that if I draw it first and then you copy it. Draw it side by side as I am drawing. So first two lines at approximately 45 degree, and keeping this as baseline, so like this. Now curve this side a little bit, and other side this way. Okay, so here we have a transparent window, and here we have a plate, generally called cathode, but it is better to call it electron emitter plate. And here another plate, yes, connected to some wire or something, and there another plate called electron collector plate. Actually these two wire then get connected to some source of some high voltage. Actually it is a vacuum tube, or we can say that at very low pressure, it has very low pressure, so that we can say that it is vacuum inside it. So well, clearly this terminal and this terminal both can be connected to if this is positive, then we will connect to negative, this one to negative, and vice versa. So for that we have a little bit complicated arrangement here. Here we will attach a milliammeter also to measure current, and here we have a commutator. and we'll connect a battery, a high tension battery, this side. So that battery can be represented in two ways, one through rheostat and one, if we could write we could draw it as a variable voltage source. So either we can put an arrow here like we do in resistors, or we can put a rheostat here. So what I am doing, I am making it more simpler. So I am marking an arrow here. It means we can vary its voltage. So this is the entire setup. What are these terminals for? So this is 1, 2, 3, 4. If we connect 4 to 1, then electron emitter plate will be at positive potential, and if we connect 3 to 1, then it will be at negative potential. So actually for this experiment we have to change the polarity from positive to negative. So that is why we have this commutator arrangement here. Right now I am connecting emitter plate with this negative potential, but it doesn't mean that always it will be there. That is why I am using dotted line. Now see, when photon which incident on it will strike this surface, then photoelectron will be ejected. Here I want to clarify one more thing. I have incident 3 photons and ejected 2 electrons to make you understand that it is not possible to get more number of photoelectrons than the incident number of incident photon. Even generally we get less number of photoelectrons. Why? It is because some of the electron will collide with each other and lose their energy. They will not come out. So that is why it is general belief that generally and theoretically we can say that number of photons, each photon will eject an electron, but it is not practically possible. So we receive less number of photoelectrons. We call them photoelectrons. So if we have connected it to negative potential, then these ejected electron will pushed, and the collector plate is at positive potential. So it will attract these electrons, and there will be a photocurrent in the circuit. Next thing, if we reverse the direction, that is if we connect 4 to 1, that is ejected electron, and here it is positive plate, so electron eject and attracted toward this plate, or in other way we can say that this plate is at negative potential then, so electron are emitting and being repelled from this collector plate. At that time current will drop. We are thinking that at the very next time as we make it negative, no electron will reach here, but still there will be some fast moving electron, they will still reach this side. uh, I can tell you the similar situation, like if we throw something upward, that object is being pulled toward the earth, but still we are capable to throw it in upward direction. So in the same way, it is being pulled toward this emitter, or we can say it is pushed away, but still few electrons would be there which will reach this collector plate. So this is the experimental setup, and here not only voltage and current, but there are two more factors. We know that by changing voltage, current will be influenced, but there are two other factors also, and one of the factor is intensity, and other factor is frequency of light. So how these two factors will affect voltage and current relation? So all right, two names of scientists I want to mention here. They are Leonard and Hellwash. Maybe He, I don't know. Hellwash. Oh, sorry. SCH. Hellwash. So sometimes these names can be mentioned there. They can ask question that draw the experimental setup of Leonard Hellwash experiment, or similar kind of statement they can mention, and at that time you might be getting confused that which chapter they are talking about. So actually they have not exactly done this type of experiment, but similar to that. So I'm not going into the history of that experiment, so I will make a separate video for just the to uh, for some curious students who want to know. Anyway, uh, so let's get back, and let's see how they have performed this experiment and what were the experimental outcomes. So experimental outcome, I'm writing in, first I'm drawing a graph, and afterward I will list out the experimental outcomes. So first thing, IV graph, IV or VI, I generally write IV, I on y-axis, V on x-axis. IV graph for photoelectric effect. At constant intensity and given frequency. A suitable frequency, actually, given frequency, uh, above threshold frequency. So actually, if radiation is of frequency less than threshold frequency, then nothing will happen. So for till the end of this video, whenever I talk about the frequency of incident radiation to produce photoelectric effect, I meant any frequency which is above threshold frequency. So each time I will mention that, but if in some case I do not mention it, so it should be considered as if I am talking about the frequency which is above threshold frequency. So here we have this graph. This is V, called plate voltage, or actually collector voltage, electron collecting plate voltage, electron collector plate voltage, voltage. And this is photocurrent. So and keeping intensity constant, frequency constant, and frequency is greater than nu naught. So these are the specification. On the basis of that, we are going to draw this graph. So the graph goes like this. So it is a typical graph. It can vary. Its slope can vary, but you can see it is not a perfectly linear one, and here we have a constant value for that. So I'll mark different parts. It is called saturation current, IS, saturation current. So there is another point at 0 voltage, there is some current. We can call it short circuit current, but we generally don't make any comment on this current. Here we have a negative voltage. Even at negative potential, as I told you, that if we put negative potential on this plate, then we expect that no electron will reach here, but still there are some highly energetic electron which reach this plate and form photocurrent. So in the same way, if we make plate potential negative, still there is some current, and that current becomes zero at a particular potential called stopping potential. So first we need to just define these terms, saturation current and stopping potential. Afterward we can proceed. So first is this saturation current. The maximum photocurrent at a given intensity of light is called saturation photocurrent. So the minimum negative potential at electron collector plate, on कहना चाहिए, on electron collector plate in photoelectric experiment, at which photocurrent becomes zero, is called stopping potential or cutoff potential. This, when photocurrent becomes zero. So one more thing, this stopping potential potential is the measure of kinetic energy of photoelectron. That is, kinetic energy maximum is equal to EV naught. The question is, why is there this saturation current region, and why is there this non-zero current at zero voltage? So right now I'm giving just verbally answer, and in question answer section, when I upload important question, I will include this question also. So in that at that time you will get these answers in written form also. So saturation current, well, you can see at a particular voltage after which we are increasing voltage but current is not increasing. So when all the number of photoelectrons are being collected by electron collector plate, so at that time no more electrons are there available to form current. That is why current becomes constant, saturate. And this region, non-zero current even at zero potential, it is because there are some highly energetic electrons which are capable to jump from um, emitting electrode to collecting electrode, emitting plate to collecting plate, and therefore at even at zero potential there is some current. So first experimental result of photoelectric experiment is saturation photocurrent is found proportional to intensity of incident light and is independent of frequency. So it was found, like, if we increase intensity, and of course it is above threshold frequency, if we increase intensity of radiation, and here we have saturation current, so saturation current increases linearly. This is a direct proportion graph. Next thing, if we want to draw a graph between frequency and photocurrent, then till threshold frequency actually no photoelectric effect takes place, but above that for a given intensity it remains constant. And what about voltage current relation? So at different intensities this stopping potential doesn't change, but saturation current increases. Yeah, it is of course related to this, but in terms of voltage current relation we have to draw this diagram. So here we have stopping potential V naught, and see, frequency is greater than threshold frequency and frequency is constant here, but intensity is different. Here if I write intensity as E, so it is 3E, it is 2E, and this is E. Intensity I have used term E. Actually it can be written as I also, but I resembles with current, so that is why I'm not using that here. So all right, so next result. So next experimental result is stopping potential V naught becomes more negative when frequency of incident light increases and is independent of intensity. So if we want to draw a graph between frequency and stopping potential. See, I'm not talking about threshold frequency, it is just frequency. We are increasing frequency. So we know that up to this threshold frequency, nothing will happen, but beyond that, stopping potential goes on increasing. Stopping potential is just a number, so it is negative. So I'm putting, actually it is not required, but I'm putting a mod here so that you people would not be get confused that why I didn't use negative axis for that. So it is a direct proportion graph, but after a gap. And if we want to draw a graph between V naught and intensity, then see, if it is taking place above threshold frequency, it is independent of intensity. And now the big one, how will IV characteristic change? So here what I am considering intensity constant. Here I, here V, and I'm taking the case of two different frequency but same intensity. So it has taken place at nu2 frequency, and it was when frequency was nu1. So here it is a different stopping potential, and here we have different stopping potential. So nu2 is greater than nu1, then this had happened. So what is happening here is stopping potential. If we increase frequency, then it affects stopping potential and not the saturation current. All right, so next, third point. So photoelectric emission cannot take place below threshold frequency. For radiation below cannot take place by the radiation, by the light having frequency. Sometimes we miss these things. Having frequency below threshold frequency, that is, if nu is less than nu naught, no photo electron can emit. So last point is, so nothing to discuss here, so no graph is related. So here photoelectric emission is an instantaneous process without a time lag, without any time lag. So instantaneous means it as we expose that metal surface to radiation, it will emit photoelectrons instantaneously. So now actually that it was required. Why is this happening? So actually at that time it was required to uh, explain this phenomena. Now I want to take you to the history of physics when the quest began to answer the question whether light is a particle or wave. So, according to Newton, it is particle. According to Huygens, it is a wave. Particle nature can be explained as if we want to explain reflection, refraction, they can be easily explained by particle nature. But there are some other properties of light, and it were observed like different phenomena like diffraction, interference, polarization, which takes place in waves. But if they are taking place with light, then light must be wave. So now, according to wave theory, photoelectric effect would take place in that manner in which, according to wave theory, intensity of light depends upon amplitude. And amplitude is square actually, and it is more related to energy. So there is a relation of intensity and energy in wave theory. And second thing, frequency. Frequency is a kind of repetition. So according to higher, so if there is high frequency, there will be more vibration. There is less frequency, there are less vibrations. And frequency is related to vibrations, and vibrations is related to number of vibrating particle. And if they want to explain photoelectric effect, then they are related to number of electrons. So according to wave theory, this photoelectric effect is actually a transfer of energy, and that energy is due to the intensity of light. So even at any intensity of light, photoelectric effect will take place, irrespective of frequency. So according to wave theory, intensity is related to energy, and that is related to emission of electron, whereas frequency is related to vibration and is related to number of electrons that will be emitted. So ultimately, intensity, larger intensity will give, first thing they have said that at any intensity photoelectric effect will take place, but experimental result says something different, that photoelectric effect emission cannot take place for a frequency less than threshold frequency. This thing for that wave theory couldn't explain. Second thing, they relate intensity to energy, and energy that will be given to an electron, and that electron will be then stopped by applying stopping potential. So that energy is related to stopping potential. So intensity, they draw a relation between intensity and stopping potential, but experimental result says that intensity and stopping potential, they are independent. Does not depend upon intensity. So this also failed. Next, frequency is related to vibration of electrons, and that is why it is related to number of electron that will be emitted, and that will lead to photocurrent. and that is saturation current, ultimately saturation current. But here saturation photocurrent is directly proportional to intensity and independent of frequency. This was also failed. All of these experimental results were opposite to wave theory. Last one, it is an instantaneous process. However, according to wave theory, these radiation will incident on metal, then all the electron will get that energy, start vibrating, and after they will reach that resonant frequency of vibration, they will be ejected. So according to wave theory, there must be some time lag, but experimentally it was found that it is an instantaneous process. So that is why this wave theory to explain the nature of light was completely failed. And that is why this photoelectric effect experiment is included in this chapter, dual nature of radiation and matter. That is why then a new theory was developed that light behaves both as particle as well as wave. But the question is, how can we explain all of this? So you might be surprised that it was explained by Einstein, and for this work Einstein received Nobel Prize. It was not for E equal to mc square or theory of relativity, but for this explanation of photoelectric effect. So Einstein's photoelectric equation. He used Planck's quantum theory, and I will just in the end I will put the outlines of quantum theory briefly. So more generally, Planck quantum theory is like radiation is not continuous but in the form of small packets, and each packet will carry an energy equal to h nu. H Planck constant, nu its frequency of that photon. So according to Einstein, energy carried by a photon is transferred to electron in the metal and used in two parts. It can be, it cannot be. One, to overcome the work function number two, to give kinetic energy to photoelectron. That is, E is equal to two things, phi plus kinetic energy maximum. Why I am writing maximum? Because we are assuming that all the remaining energy is in the form of kinetic energy. It is not totally possible, but we will assume that. And because electron can lose energy by collision, by vibration, so we can't say that exactly it will be its kinetic energy, remaining energy will be its kinetic energy, but there's an approximation. But I mean, if nothing is lost, then all will be its kinetic energy. Next, okay, that's all. This is the Einstein's photoelectric equation. But now I will just elaborate this equation, because we know that E equal to h nu, and we know E equal to hc by lambda also. This is the energy of incident photon. Phi equal to h nu naught, threshold frequency, and also hc by lambda naught, threshold wavelength. In fact, kinetic energy maximum, traditional formula, half m v square, so v max square, and also ev naught. So many combination, if you put these here, so many combination can be made, but I am interested in two in two formulae. First, also h nu equal to h nu naught plus ke maximum. First is this. So h, if I take it here, nu naught equal to ke max, and h nu minus nu naught equal to ke max. And also for ke max, if we use ev naught, then the same will be h nu equal to h nu naught plus ev naught, and also then h nu minus nu naught equal to ev naught. So these are few equation, and yeah, of course hc by lambda we can also put it here, but what I want to explain from these equation, that can be explained according to these equations only. So first, now Einstein's explanations. Explanation. First one, intensity, saturation current is directly proportional to intensity. So he explained it as intensity of light depends upon number of photons incident per second. Actually, per second per unit area. intensity increases. You should write it completely. I'm using these symbols. Intensity increases, then number of photons will also increase, and therefore number of photoelectron will also increase, and hence saturation current, this will lead to saturation current will also increase, and it is independent of frequency except threshold frequency. That's all. Second, because number of electrons is independent of frequency of radiation except threshold frequency, as I told earlier. So now next, V naught becomes more negative. With increase in frequency. So now directly we can use this equation. So as per equation, photoelectric equation, H nu, see, photoelectric equation is this and it is reducible to this. Nu naught equal to kinetic energy maximum. Oh, sorry, EV naught. I'm writing it here. H nu minus nu naught equal to EV naught. So it is clear that as nu increases, V naught also increases, and it is negative, so it becomes more negative. And also this equation is independent of intensity of light. This equation is independent of intensity. That is why it does not depend upon threshold, stopping potential does not depend upon intensity. Third thing, that photoelectric emission does not take place, cannot take place, no emission, no photoelectric emission. It will not take place. Why? Because if, according to this equation, according to photoelectric equation, H nu minus nu naught equal to Ke max. So if nu is less than nu naught, then kinetic energy will become negative, which is not possible. That is why electron emission only takes place when frequency is above threshold frequency. Third point was, it is an instantaneous process. Instantaneous. So it was also explained like, as soon as electron struck by a photon, it gets ejected without a time lag. Without a time lag. That's all. That's all. Einstein did it. But the story is not over yet. There are few more things we need to discuss about these equations and all that. Look at this equation. Y equal to mx plus c. It is an equation of a straight line. In fact, I am putting negative because this is what we have here. We will be interested in this entire discussion. So when x is 0, value of y will be minus c, somewhere here. And other than that, it will be a straight line. So now correlate this with photoelectric equations. First I will set the equations like E equal to phi plus Ke max. So h nu equal to h nu naught plus Ke max. If I write it in this way, kinetic energy max is equal to h nu minus h nu naught. And then if I correlate it with this equation, the graph will look like this. This is kinetic energy, this is frequency, here we have h nu naught, that is this negative intercept. If we take its positive value, then it will be phi, and this will be the graph. Here we will have this nu naught. So, and see, m is slope of this line. Here m is h, so its intercept will give the value of phi, and its slope will give us the value of Planck's constant. And if instead of kinetic energy I use EV naught, then V naught will be equal to h by E nu minus h nu naught by E. In this case, if we draw a graph between V naught and frequency, then the graph will look like this. Once again, this time it will give the value of h nu naught by E, that is phi by E, and its slope, here intercept, I am writing it I, int, that will be better. Intercept will be h nu naught by E or phi by E, and its slope will give the value of h by E. So by this we can explain this negative region, this negative energy region, which is in fact that work function which is required to eject electron. Now it entire this scenario will become more complicated if I replace nu by c by lambda. Then V naught is equal to hc by E 1 by lambda c by lambda. I can write it like this, minus h c by E lambda naught. Not required this part, but and now if I draw the graph between V naught, and remember 1 upon lambda, it is inverse proportion, but if I take 1 upon lambda, entire 1 upon lambda as a variable, then it will become a direct proportion. See, this 1 upon lambda, consider it something else, then it is in direct proportion. If I write it here lambda, then it is inverse proportion, so it is in direct proportion. And once again same thing, there is minus hc by E lambda naught, going like this. Once again there are some value like 1 upon lambda naught, which corresponds to that those values of okay, and see here slope is hc by E. So these type of question can come in the exam. And see, one more thing, each time the slope is a constant. This constant is independent of choice of metal, choice of material. So for all the metals, the slope will same. I have once seen a question in a competitive level, and there were graphs given like this. I think it was such question, and one of the option was there is an error in the question, so that was the correct option, that question, so that was purposely made. So now let's move to Planck's quantum theory. So here is Planck quantum theory, and just you need to be aware about it. No need to memorize these things, but you need to be aware about it. So photon picture of radiation mainly. So first thing, energy carried by radiation is not continuous, means it is not like that it can be infinitely divided, but discrete. It has some minimum values and integral values of that, and it exists in the form of small packets of energy. Energy of each packet of photon is directly proportional to frequency of radiation, so E equal to h nu, h Planck's constant. Energy of radiation exists in the form of integral multiple energy of a photon, so E equal to h nu for single photon, and if there are number of photons, then this is integral multiple. Photons of same energy are alike, same energy or frequency are alike. So so it means if we talk about photon of red light, So all of those photons which lies in that region will look alike. And see, now we have to draw a clear margin for that we know that for particular frequency we have a particular wave. So in fact, for that red region there are also a number of frequencies in that region. So for a particular frequency we have photons, and for that frequency all the photons will look alike. uh, all photons travel with speed c equal to 3 into 10 to the power 8 meter per second. We generally call it speed of light, but light is also a photon in vacuum. Photons have zero rest mass. Moving photon have mass m equal to E by c square according to Einstein's uh, mass energy equivalence, and here we can also write it h nu by c square. And momentum, it also carries some momentum, so which is given by E by c, or h nu by c, or h by lambda. So this is all of it, and all in all, the big picture is that these light which we usually see and all the radiation, I would say that entire electromagnetic wave spectrum corresponds to some photons, associated with them to carry their energy, and therefore this quantum theory is of a wide range. It is not limited to that visible light and all that. So this is all about uh, dual nature of radiation and matter. And after that there is de Broglie hypothesis, which is actually pronounced as de Broglie hypothesis, and I have made a separate video for that. Go to watch that video also, and I will put its link in the description. So students, I hope this lecture was very much informative for you people, and wait for my next video, in which I will include some questions and I will give their solutions, which are important as far as CBSE boards and even ICSE board, I mean board exams, are concerned. So stay connected, and that's all. Bye bye.